All right. Hello, everybody. I'm Carsten from Bosch. With me here is Mikael. We're going to talk about ROS2, and we do it in the most insanely way because we don't want to do live demos. Now we figured out we're going to do this on 640 x 480 resolution because like somehow the HMI doesn't work on Mac. Plus we have like 500 people here in the audience and 1,000 times the live stream open, so looking forward to it. We do have slides, and we have stuff prepared for you to actually do that all at home by yourself. What you're going to do is like you need a ROS2 installation. You find the installation instructions here on the link, plus a little bit of like an overlay workspace, and you find code which we're going to present today under that link. It's not an official ROS2 maintained code, so it's private on my repo. You can build it, and then you can follow all the steps we're going to show. All right, so let's see what's happening. Cool. Is that readable somewhat? I know we're going to show a bit of code and like quite some terminals, so I hope this is going to be readable on all the monitors as well. But so generally, what you want to do if you start with ROS2, you want to create your own first package, right? And so the question is like, how do you do that? And what you're going to do is like we have commands for this in place. Basically, everything starts with ROS2, then a verb, and then you can execute your commands. In this case, we want to create a package, so we do ROS2 package create, and it gives you, and I'm sorry for the format here, but like it gives you a bunch of stuff you can do, so you can get your dependencies and these kind of things. We want to do all of this. I prepared that. Basically what we're going to do, we create a first package, we give it some dependencies like RCL-CBP because we're going to develop our nodes in C++. Then we give it a node name, my first node, a library name, and that's about it. Right? So a bunch of stuff is happening. If we open up the best editor in the world, we see that we're going to have now our first package, right? So we have some includes, we have some source files, and then if we look at the CMake list, that's the default CMake list we have for ROS2. So basically we default to C99 standard, to C++ 14. We find all our dependencies, in this case like the RCL-CBP, what we said. We have our libraries. We have some definitions to make that actually also compile on a Microsoft compiler. And exactly, so the executable. The other thing I want to highlight here is that we have, by default, we have some linters and coding styles we expect for ROS2. So you can test your package against our coding styles, right? So by default, obviously, we don't generate any G-tests and these kind of things. You can do this by yourself, but the linters are there. And so, oh boy, there goes your best editor in the world. If we now compile all of this, we do call const build, and we give it the package to select, for example, like my first package, right? So we do all of this, we compile this, and if we now do ROS2 run, we can actually execute all of this, right? So let's go back for this. If we now look in our main node, so actually what we say is like my first package, hello world, right? So let's say we have the format out of place, some indentation which is wrong. We can test all of this. We say call const test, and we see, okay, there's a complete battery of tests running right now. But like essentially what's happening now, you say, okay, classified failed, and what you see is like eventually there's some diff. Here. So it says, okay, something is wrong with the indentation, right? So that's cool. So now we have our first node, our first packages, we can work with it. But let's switch gears a little bit. So what we actually want to do now, we want to create our own robot. So we have a robot application, we're going to create a robot for the conference here. So we name it confbot. So a typical thing what you need for that, we created a bunch of packages, and this is now all on that GitHub repo we showed at the beginning. But so essentially, like we created a bunch of packages such as like bring up, a typical package where you have your launch files, configurations, then a description where your URDF is in there, a driver, which is like the algorithmic part for moving your robot, security, Mikael is going to talk about this later on, sensors and tools, right? So the way we're going to launch that is we have a launch file. And so the first surprise here is like, okay, it's not an XML format anymore, it's going to be Python. But essentially what we do, it's the same thing. So we get our UIDF from our workspace, then we get the robot state publisher, the driver, a twist publisher here, which is essentially emulating your joystick to moving around, and we have sensors, a laser, and a safe zone publisher, some markers. Okay. If you want to know more about all of these launch things, there's a talk coming up from William. He's going to explain a little bit more on this. So the way we're going to launch this now is, where's my terminal here? We actually say, launch. So we launch this, and again we see, okay, some stuff is happening. But now how do you actually introspect all of this? Is like, we have a new command here, ROS2 node list, and we see, hey, there's our nodes, right? And just for completeness, I mean, like, most of you know that by now, but there's no ROS core running anymore, right? I just launched up my ROS2 launch file, and that's it, and there are my nodes. So we have the launch file, we have the robot state publisher, the driver, the publisher, and so on, right? The second thing we can do now for introspecting is we list all our topics, we give it a -t here in order to see all the types associated with the topics. And so we have like, okay, our command velocity, which is set to twist, and a bunch of stuff like our safe zone for markers and these kind of things. So let's say we want to see what's happening, we can do command line echo. And we see, hey, something's happening here, right? But the actual way of introspecting all of this is like, we start obviously, we want to introspect this visually. And so for this, we start ROS2, and that's what I expected. So we have our nice conference robot, right? And here a big shout out to Cole, who actually put me that URTF together. So we have the Madrid logo on our robot with a turtle operating here in a circle in a safe zone, and we have this dangerous shark who's trying to do bad things to our turtle. But now if we look at it, we actually had like a laser scanner, right? But we don't, like, you can see that, but there's no laser scanner here. And we see, okay, hey, there's like, it's from 0 points, from 0 messages, and so like, what's happening here? And for this, what we did, and you can look at it in the code later, but so we developed our laser driver as a lifecycle node. And reasons for that, for example, you want to make sure that device drivers are generally like set up correctly and started correctly, that you can then launch your algorithm on top of that, right? Because you don't want to, you want to make sure that your algorithmic part only operates when all the device drivers are fully set up. And the second reason for lifecycle nodes for device drivers is that maybe you want to just shut them down or like deactivate them during runtime to actually to save energy, right? And so the way we can introspect these lifecycle nodes now is we can lifecycle list, and you see indeed our laser node is actually a lifecycle node. Now what we can do, we can also just ask the state of that. And we see it's in a state unconfigured, which makes sense because it's the default state. Now if you want to configure this, we say ROS2 lifecycle set, we configure our laser, and we see on the right side, on the left side, you can see that the output is like, okay, our laser is now configured. If we want to activate this, we execute the same command, and it's activated now. Let's see if our ROS shows us that. And we see already, okay, now all the messages are there, and we have our robot set up, right? A second thing we want to show here is that we have parameters in place for our twist publisher. So by now it's publishing with like a velocity of 0.1 or something, and we can actually ask for params. And so in order to do this, we see, okay, if you do ROS2 param list, you actually see, okay, all the nodes, but there are no parameters attached to it. A new thing here for ROS2 is also that there's no global parameter server anymore, right? So every node has their own parameters attached to them. And now we can do ROS2 param set, and we set it for our twist publisher. And we set speed to 0.2. Basically what we did is like we just operate our turtle not double as fast, right? So these are taking into account on runtime. We can set it back to 0.1, and it's all good. So that's basically how you would set up a robot. And so now basically what we have is like we have our markers, we have our lasers, device drivers, everything in place. But now I hand it over to Mikael, and I keep typing though. But Mikael will show you now what you can do now as a next step once you have that in place, which is not a big surprise. It's like it's a robot, right? We all know that. What can we do with ROS2 to actually harden the system, make it more interesting?
Thanks, Karsten. So yeah, Karsten is going to be typing because I can Vim, but I cannot Mac. So that's going to be easier. So we're going to look a bit at some of the code just to have an idea of how the nodes are like written. The main first thing we want to show is that here we are actually in a header file. That's our twist publisher. So it's a class that we declared that is inheriting from our base node class. And that's how we expect most of the nodes to be written. And the main reason for that is that then we can compile each of our nodes as a single like shared library that we can then reuse. So if we look at the main, this is on the top side, you can see the main of the driver is the same on both. Yeah. And if you look at our twist publisher, we're going to see that the main are actually almost identical. So all the parts that are handled are executable is really just starting our CLCPP, instantiating a node, and spinning on it. And all the logic is going to be in the header. What makes that very powerful is that it makes it much easier to actually like compose nodes and bundle nodes into the same executable. So in this case, if we look at this config all, we can see that like the structure of the main is exactly the same. We just need to include both of our nodes headers and instantiate two nodes, add them to what we call an executor, which is going to be like the structures that will be used to spin your node, and then just call spin on it. So that's what we call manual composition. There are other ways to do composition. I think William is going to touch on that on his launch talk as well. But that's just to give an idea of like how we expect like a node structure to be like. Switch back to. So we still have our turtle running in circle in its safe zone. So that's something you may have faced a few times developing with ROS1 when you have several people on the same network and publishing using ROS tools to publish messages. So in this case, what we're going to do is that, what if someone tries to publish on command velocity? And so in that case, we're just going to publish a different spin. And if we look at our RVs, someone took control over our robots and actually threw it in the shark's mouth. We don't have the animation for the turtle getting eaten, but that's the idea.
Shut down. It's too violent.
And so the main question is like, how can we prevent that? And in ROS1, we could have like different master URI, but as soon as someone is on the same network and talking to the same master, we didn't really have a way to work around that. And so what we did in ROS2 is that we have the ability of like, because we're using DDS underneath, DDS has a security specification that allows us to define which nodes are allowed to join the network, what they're allowed to do, these kind of things. So here what we're going to do is like we're going to show on the ROS side, we don't do like security ourselves, we just provide and retrieve all the security artifacts to feed to DDS, and DDS handles all the encryption authentication. So in this case, we don't want the user code to change. You should not have to change anything in your node to be able to use security or not. So right now it's handled by environment variables that are listed here on the left side. And the main thing is that these three environment variables are like handling all the configuration, which is basically we have a security enabled environment variable, something to define like what is the global behavior, if we should like enforce and deny any access to the network, or if we could have a more like permissive node, and mostly the path where for this node or for this shell we can find the security artifacts. And so we're going to just set these environment variables, and we're going to restart our application, our launch file, and RVs. And if everything goes well, we should not see any differences. So the only difference in what is happening here is like all of these nodes. Oh, no save zone. Okay. Yeah, there we go. So here you see it's exactly the same nodes that have been launched. Exactly the same behaviors. The only difference, like all of them had to actually like authenticate themselves to the network and to be able to talk to each other, like challenge each other and set up keys. And so all the data being sent right now is encrypted. We're not going to show Wireshark because it's going to be challenging on a live demo, but everything is encrypted here. And so now if we try to take control over our turtle again and try to throw it in the shark's mouth, we're going to see that the node cannot even start. It's not allowed to join the network, so this node is just directly rejected. And so you can see that with that security error and pretty verbose error message. So that's good. So what we can see here is that the node names is what define like what node is allowed to join or not. So that works for, like, for example, ROS topic pubs that we didn't allow. But if someone reused the same executable as we did and just remap the node name on command line using __ node, we have the same behavior, not allowed to join. So all that is good. That allows mostly to prevent from people on your network spawning new nodes interfering with your system. But it doesn't protect you from people modifying your nodes or your trusted executables. And there are several ways to protect that on the system level by like signing binaries, but we're talking about mostly network security here. And so what we're going to look at is like how can we provide additional configuration and granularity on like what is a node allowed to do. So right now our Twist publisher, our safe zone publisher is just allowed to publish what is the safe zone our turtle is allowed to navigate and what is the zone where that's the shark territory. And so we're going to define using this YAML format what are the permissions that, what is the node allowed to do. And so here, it has only two things it can do. It can only publish on two topics, which is the safe zone and the danger zone. So now what we're going to try to do is that we're going to modify our small Python executable. And this is mostly to emulate that someone is like taking control and successfully injected code in our system. And so here we can see that we just decided to create a new publisher and try to make our safe zone publisher take control over the robot and publish on command velocity. And so now if we try to run that node, we're going to see that it's going to fail to start. The main thing is that the node is going to be created, it's going to start creating its publishers, and as soon as it's going to reach a publisher that like, is not allowed in the policies we defined, it's going to be like, prevented from being created. So here we can be more robust to code injection and modification. If any node that is doing something that is outside of its scope, we can actually prevent it and catch these errors and have like, some fallback behavior as well. Okay, so if we want to recap real quick, if you want to walk through it at home, so we just installed ROS2, pulled our small repository with a few packages, and built it. So that's our overlay workspace. That's what we use for this entire demo. Then we saw how to create a package, how to specify library names, dependencies, and how to get all of this bundled into package.xml and CMake list, how to run, like how to build our code, how to run our code, how to run our tests. We saw what launch files look like, how can you specify the number of nodes that will be in your launch file, how to set up where the output is going to be, on the screen, on the console, etc. We saw some of the ROS2 command line tools, how to introspect a running system. So most of them are pretty, like, you should be pretty familiar with them because they're pretty similar to ROS1. We're trying to have like a similar experience. So ROS node list, ROS topic list, ROS topic echo, ROS topic pub. Then we saw that we have RVs natively on all platforms. Like Andreas is going to talk about this later, I think. But so as in, we didn't have to do anything specific or run Mike's magic script to get things to compile and run on Mac. And a bit more of command line tools, how to interact with things that are hosted on the node itself. So how to modify parameters on a specific node, how to list them, modify the system. We saw the idea of lifecycle node, how to see which lifecycle node are running, their state, how to modify them, how to interact with them, how to shut them down. An idea of what the structure of like composing node is like, and mostly how we expect to write nodes in the ROS2 ecosystem, and how to then compose them. Then we looked a little bit on like how can we tamper with the system if we have access to the network. So how an unsecure system can be taken over, and then how we can try to work around it. So if we go, we can see we have just this very simple set of environment variables that allow us to define, like, to enable security for a specific set of nodes. and how to relaunch our demo with that. We saw different ways that a node that's not authenticated would fail. So in this case, nodes that don't have the right name or don't have the right executable would fail. And we also looked a bit deeper into how the configuration is like. So in this case, how to define policies for a node or a set of nodes in a YAML format, and how to generate them. So that part we didn't show you, but the command at the bottom is actually what allows to generate all these security artifacts. The next slide shows you just a small extract of like what these DDS XML files that are generated look like. We looked how we can modify existing code and how we can like catch these issues by defining policies, and so how it would actually fail to run. If we try to run them, we're going to have like detailed error messages of like which topic and which publisher is not allowed, etc. And so that is just a subset of ROS2 features. There are many other things that are available since previous releases or current release, Bouncy. I listed a few of them here, mostly to give an idea. I think they're relevant for some like existing ROS1 users or just new ROS2 users. So the ability of being able to bridge communication between ROS1 and ROS2 via the ROS1 bridge, to be able to set up efficient intra-process communication. So here we saw how to like bundle nodes in the same process, but then we can also enforce that like all these nodes should use only shared memory or intra-process communication. So basically bypassing all the networking part and the DDS part of the stack and just stay in the RCL CPP level and just pass unique pointers around. How to set up node parameters via YAML files. We didn't say, we just see how to modify them. And many other command line tools that we're starting to put together. And so this is the state of Bouncy. Last release was in June. Our next release is going to be in December, and so on Master today we started working towards that release. So I listed a few things we've been working on to give an idea of like where we're going. So implementing some like higher level packages that are very useful for data processing, for example, message filters and image transport. For starting porting Gazebo ROS packages to ROS2, so to be able to actually use Gazebo with ROS2 directly. There are several plugins that have been ported, and I put a link there if you want to follow the progress. That's still like work in progress, moving on a daily basis. We started implementing ROSbag in ROS2. So a native ROSbag, not something that goes over a bridge. And if we're lucky, we'll have a lightning talk. Karsten and some colleagues will do a lightning talk about it. Otherwise, just ping him anytime. And improvements around ROS time, like being able to use simulation time everywhere, these kind of things. That's, again, like a subset. Crystal, like the roadmap is evolving as we get more and more contributors. I've seen recently, like there is a technical steering committee for ROS2 that is now providing also resources to work on that release. So if you want to see what's the state and what is the plan for Crystal, go to that link. Don't necessarily stop on what is on these slides because it's moving. There are many, many new things and exciting things coming, so just follow on the wiki. And I think we're on time. Perfect, thank you very much. And if there is any question, we'll take them happily. Oh, I can give that back.
Is there any way for avoiding DOS attacks?
So the question was like whether we have security in place to avoid DOS attacks. Is that correct? I'll let Mikael answer this.
Yeah, so one of the main things for denial of service is that we don't need to process, like having this way of specifying what is allowed to join the network is already preventing, you don't have to process the packets of any node that is like not authenticated. These are going to be discarded automatically. So you don't have to actually unpack 1 gigabyte, I don't know, like point cloud message to find out it was just tempered and not allowed. So that's one way to actually work around it. There are several other approaches. I think Gerardo and Rafin may be talking about it later today. We have a ROS2 security talk today, so you may have a bit more context there. Yes?
Is there any way for reconfiguring the permissions of an outline?
So the question is, can we dynamically reconfigure the permissions of a running node?
Yeah.
So currently, no. The main thing is that permissions are passed to the DDS, like the underlying DDS layer, at node creation time, at like DDS participant creation time, which is basically ROS node creation time. And so at that point, these artifacts are loaded and stored. And so if you modify these files later on, you cannot tamper with whatever security configuration has been made. Then it could be done in the future if we could provide a mode to allow you the same way as we could do for changing, I don't know, many topic names or things like that may require you to recreate DDS entities. We could provide a way to reconfigure static quality of service and security at runtime, but that still means that under the hood you actually kill whatever entity you're using to create a new one.